All right, today we're going to tackle a really core concept in computer science, recursion.
So a function that calls itself, that sounds like madness, right? It just sounds like a recipe for an infinite loop, a program that's going to crash. But believe it or not, recursion is actually one of the most elegant, most powerful tools we have for solving really complex problems. The best way to get our heads around this is with a simple analogy. Think about Russian nesting dolls. You pop one open, and what's inside? A smaller but basically identical version of itself. You keep doing that. Open, 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 until you get to that last tiny little doll that doesn't open anymore. That right there, that's the core idea of recursion.
Okay, so here's the more, formal definition. Recursion is just a problem-solving technique where a function calls itself, but with a simpler version of the original problem. And it keeps doing this over and over until it hits what we call a base case. That's our final little nesting doll, the point where the problem is so simple it can be solved instantly.
So yeah, let's really dig into this Russian doll principle. It's all about solving a big, complicated problem by first solving a smaller, identical version of it.
Now, to stop this from becoming that infinite loop we were worried about, every single recursive function has to follow two golden rules. And I mean, these are non-negotiable. You mess these up, and it all falls apart. And here they are. It's actually super simple when you break it down. Rule number one, you have to have a base case. That's your stopping point. It tells the function, okay, we're done, no more calls. Rule number two, with every single call, you have to get closer to that base case. The problem has to get simpler. It must get smaller each time.
I love this quote because it just hits the nail on the head. Without that base case, your function is just lost. It's like being on a road trip and just asking, are we there yet forever? Because there is no there. The base case is your destination. Forget it, and you're headed straight for a crash, what's called a stack overflow.
Okay, so this probably brings up a question for you. If a function is calling itself, and then that call calls itself, how on earth does the computer keep track of where it is? Well, let's pull back the curtain and look at the magic behind the scenes, something called the call stack. The easiest way to think about the call stack is like a stack of plates, or maybe sticky notes. Every time your function calls itself, the computer scribbles down a quick note, here's where I was, here are my current variables, and slaps that note on top of the pile. It's a way to remember its place. All right, let's make this real. We're going to trace a classic example, calculating the factorial of 3. So the first thing that happens is our program calls factorial of 3. But wait, factorial of 3 can't give an answer yet, right? It needs to know what factorial of 2 is first, so it kind of pauses itself, and its state gets pushed onto the call stack. So now, from inside that paused function, we call factorial of 2. A brand new frame for that call gets put right on top of the stack. But same story. Factorial of 2 can't finish until it knows the answer to factorial of 1. Okay, one more time. Factorial of 2 calls factorial of 1. Its frame goes on top of the stack, and boom, we've hit our base case. We know the factorial of 1 is just 1. It doesn't need to call anything else. It can finally give a concrete answer. And this is the really cool part. Once that base case returns a value, the whole process reverses. The stack starts to unwind. Think of it as taking that top sticky note, getting the answer from it, passing it down to the note underneath, and then crumpling it up and throwing it away. So that factorial 1 frame says, hey, the answer is 1, and passes it back to the factorial 2 frame that was patiently waiting. Now a factorial 2 can finally finish its job. It goes, okay, I need to do 2 times that answer, so 2 times 1 is 2, and it passes that result back up the chain. And we're almost there. The factorial of 2 frame passes its answer, 2, all the way back to the very first frame we started with, factorial of 3. And now it has everything it needs. It calculates 3 times 2, gets 6, and that's our final answer. The stack is empty, the job is done. So you see, the really crucial thing to get here is that the call stack is like the computer's short-term memory. It's what lets a function pause, go off and solve a smaller piece of the puzzle, and then come back and resume exactly where it left off. That's the mechanism that makes this whole recursion thing work. Okay, so now that we know how it works, let's talk about when we should use it. Because while recursion can be amazingly elegant, it can also be a trap. It can be dangerously inefficient if you use it on the wrong kind of problem. Yeah, this really shows the two faces of recursion, right? On one side, you have divide and conquer problems. Think about searching through a phone book. You can recursively split it in half. For things like that, it's a dream. But on the other side, you can get into this nightmare of redundant calculations, where you're just solving the same problem again and again and again.
Just look at this chart. A recursive binary search, it's lightning fast. We're talking O log n efficiency, because every step cuts the problem in half. But then you look at a naive or simple recursive function for Fibonacci numbers, it's O to 2 to the n. It's an exponential disaster. And the reason is simple. To calculate, say, fib of 5, it has to calculate fib of 4 and fib of 3. But to calculate fib of 4, it also has to calculate fib of 3. You end up redoing tons of the same work. So, with all that in mind, how do we decide when to actually use it in the real world? This is a huge question, and it's something that comes up all the time in coding interviews. This table is a pretty good cheat sheet. Look, for problems that have a naturally recursive structure, like file systems or family trees, or any kind of tree data structure, recursion often leads to code that's way cleaner and easier to read. But for something simple, like just counting from 1 to 10, a simple loop, what we call iteration, is almost always going to be faster and use less memory.
Okay, so let's boil this all down. If you're going to walk away with anything, remember these key takeaways. 1, always define your base case first, before you write any other code. 2, make absolutely sure that every single recursive call is simplifying the problem, getting you closer to that base case. 3, don't forget the call stack. It takes up memory. If your recursion goes too deep, you'll run out. And 4, and this might be the most important, always ask yourself, could I just do this with a simple loop instead? Sometimes the elegant solution isn't the best one.
So now that you really get the mechanism behind it, think about this. What common algorithm do you think is the most elegant example of recursion? Because in the end, recursion isn't just code. It's a way of thinking. It's about training your brain to see the smaller, identical patterns inside huge, messy problems. And once you can do that, you've unlocked a seriously powerful new way to solve things.